Okay, let's go. We're going to continue with chapter 6. Systems of ODs. So last time we talked about the competition model with those two differential equations that kind of are like logistic equations. We talked about the competition table and how to fill that out. Now I want to show you how to actually solve a problem. There we go. So this is going to be sort of like how I did chapter 4. I'm going to teach you how to do stuff while doing an example, and then we'll do a few more examples. I have 4 in total, so let's actually get to it. So for the following, A, find the competition table. Determine the system is competitive B, perform, and this is the part I'm going to teach you today, qualitative analysis. To analyze the long-term behavior. And our first example is the following. dn1 dt is equal to 0.2 and 1 times 1 minus and 1 over 100 minus n 2 over 50. dn2 dt is equal to 0.1 and 2 times 1 minus n 2 over 25 minus n 1 over 200. 0.2, 1 minus n 1 over 100, and 2 over 50. Well, actually, you mentioned this was 0.15. Doesn't matter. And 2, 1 minus this over 25, that over 2. Okay. Boom. Part A, competition table. How do we fill it out? Okay, so what number goes here? The effect of 1 on 1 is 1 over 100. The effect of 1 on 2.
The effect of 1 on 2.
1 over 200.
1 over 200, right? This is how N1 is affecting species 2. 2 on 1.
Species 2. 1 over 50.
So you look at the effect of species 2 on species 1.
1 over 50.
Your species 2,
1 over
its
50.
effect on species 1 is 1 over 50.
Yeah.
And now I look for 2 on itself.
1 over 25.
Is that 1 over 25? So, is this competitive or not? Which one of these are bigger? 1 over 100 or 1 over 200?
1 over 100.
1 over 100. 100 is bigger. What about these?
1 over
1 over 25. So what can we say about this?
It's not competitive
How do you know?
because if one's greater than the others.
One is beating up himself more than he's beating up 2, right? So there's no competition, right? if you want, you can even analyze it further. You can talk about the total damage on each species, where you just add this one and that one. So that'd be like 0.3. And, right, because this is 0.01. This is point what? Is that 0.02? So yeah, we have one over what? What do you say?
So instead, I mean, species 2 is going to survive.
We'll see. What's the effect here? 1 over 200 is what? 0.005. 1 over 205. Point what?
0.4.
So the effect over here? 0.045. Right, so you see overall species 2 is actually taking slightly more damage, right? So we'll see how that turns out. But here you can say from this it's non-competitive.
Why?
Remember what competitive means. Each species beats up the other species more than it's beating up itself.
Okay.
One is beating up itself more than it's beating up species 2. So it's
That's what a
non-competitive.
higher number means.
How can you tell when it's beating up?
This number represents the damage it's doing. Right?
Oh.
Because you're subtracting from its growth rate. So the bigger this number is, the less it will grow.
So 2 is damaging itself.
So
more than
how species 1 is growing is slowing down its own growth rate more than how species 2 is slowing down its growth rate.
Okay.
So they're suffering more by themselves, competition among themselves rather than competition with the other species. So it's non-competitive. They're beating themselves up.
Okay.
Okay. Now,
What about
let's-
2? Sorry, what
Same
about
thing,
2?
right?
2 is beating itself up more than.
It's the same
Yeah.
in 2, but it doesn't matter. Once one of them is beating up themselves more than the other, it's non-competitive.
Okay.
Okay.
So now B, here's the new material. Qualitative analysis. Step 1. Very similar to the last one, we're going to find the steady states. We're not going to find inflection points, we're not going to need it right now, and you'll kind of see why. But we're going to find the steady states. Remember how we find steady states?
Make the derivative equal to
The
0.
derivatives equal 0, but now we have 2 derivatives equal 0.
So that means.
Right? So I need dn1 dt equals 0, and at the same time dn2 dt equals 0. Therefore I have 0.21 n1 times 1 minus n1 over 100 minus n2 over 50 equals 0.
So it means
And
here
I have
is 0.
1 n2 times 1 minus n2 over 25 minus n1 over 200. That equals 0. All right, so remember these are your equations. This is equation 1, this is equation 2. Remember what we did?
Yeah. So it's 0, 25, and 200? Or-
No. How do we solve this? Simultaneously, remember.
Take the
Eh.
0.21 and equals 0.
It's not point
Then
21. It's
add
just
1 equals 0 and then the other side is equal to 0.
I'm not sure.
I thought from when you told us before that you could make this one equal 0 and then the other side, the inside would always equal whatever the denominator is or the denominator is.
No,
Can you
it's not
add
what
the
it says.
2 together? And then that
You
would get
solve the first one equals 0. You have a product of things, right? You have this times this equals 0. It means one or the other is 0.
Okay.
So you solve for one, you substitute in the other. That's what we did last time when we had x's and y's. So from equation 1, I have 2 situations, right? I have either n1 equals 0 or 1 minus n1 over 100 minus n2 over 50 equals 0. Right? This I can simplify a little bit. I can multiply both sides by, say, 100. I get 100 minus n1 minus 2 n2 equals 0, or in other words, n1 would be equal to 100 minus 2 n2, right? So either n1 is 0 or n1 is done. And then we deal with each situation separately, right? So in equation 2, if n1 equals 0, what are the consequences? I'm going to go to equation 2, and I'm going to plug in n1 equals 0. So I'm going to get 0.1 n2 times 1 minus n2 over 25 equals 0, right? So then I would get either n2 equals 0 or n2 would be 25. This gives us two steady states, right? I can have 0, 0 and 0, 25. Right? Think of my n1 as the x value and my n2 as the y value. Right? So if my x value is 0, my y can either be 0 or 25. And so I get these 2 points for this situation. Now I just try the other situation. In 2, if my n1 was actually equal to 100 minus 2 n2, what happens when I plug that into this guy? Then I would have 0.1 n2 times 1 minus n2 over 25 minus, so this whole n1 here, I'm going to replace it with that whole thing. So this is 100 minus 2 n2 over 200. So now I have two situations. Either my n2 is 0 or this equals 0. I can multiply both sides here by 200, so I would have 200 minus 25 goes into 200, 8 and 2 minus 100 plus 2 and 2. So how do I solve this? What happens?
6 and 2.
So I have minus 8n2 plus 2n2, that's minus 6n2, which I bring it over here, so I get 6n2 is equal to 100, so that my n2 is 100 over 6, or 50 over 3. And that would give me two other situations, right? So n2 equals 0 is one of the possibilities, which means my n1 would be 100 minus 0. So this leaves me with the 100 comma 0 steady state. And if I have n2 equals 50 over 3, my n1 would be 100 minus 2 times 50 over 3, which would be 100 minus 100 over 3, which would be 200 over 3. So I have 200 over 3 comma 50 over 3.
And this is just one step. This is just
That's
a steady
step
state.
1. So yeah, find the steady states. In principle, it's the same thing. You said that 0 is equal 0, but now you have a simultaneous set of equations. So you solve for one. Just break down one of them as much as you can and substitute that into the second one, and just read out all the answers. So ultimately here we have 4 steady states, these 4 points.
Jhevon,
Can you go over it quickly?
the equations that you put under n2 is equal to 0, you got those from the derivative equations? That's
Yes, from this
yeah.
equation.
Okay.
Okay. So to run through it again, Find the steady states, you set each equation equal to 0, right? You get this set of equations.
Okay.
I'm going to use the substitution method. So I'm going to take something I know from here and substitute it there.
Okay.
Right? So what do I know from here? I have a product of two things equals 0. So I set each factor equal to 0. So I get either n1 equals 0 or this whole thing equals 0. Which brings us to here. Right? These two situations. And then I deal with them one at a time. So I pretend n1 is 0, and what does that mean? If I plug that into the second equation, I get this. And I can solve for n2s from here. So when my n1 is 0, my n2 would be either 0 or 25. And so I get these two things. Right? Because my n1 is kind of like my x. I'm doing like n1 comma n2.
Jhevon, I had a question.
Yes.
When you substituted in the 0, you multiplied the first equation by 100, right? And then that gave
Where are you talking?
1 minus
Here?
n1. No, above
On the
it.
top. Or 1
So you
minus
just
n1.
multiplied the entire thing by 100?
Yeah, I didn't get there yet.
Oh, I thought you had.
I just explained this one here,
Oh, okay.
right? So this gives me these two, right?
Yes.
And then we're done. Then you move on to the second situation, which is this, right? You consider one at a time. I pretend this is true, and I get all my answers from that. Then I'm going to pretend this is true and see what my answers are from that. Now, if this is true, I don't like fractions, so I rewrote it. So I multiplied through by 100 to kill out the denominators. 100 was the LCD. So 1 times 100 is this, 100 times that, they cancel. 100 over 50 becomes 2. And I solve for the n1 again. So then I get n1 to be this guy. And then I'm going to take all of that and plug it into n1 into here. And that's going to give me this. So now this is a whole new equation with only n2s. I can solve it for n2. I have this times this equals 0. So that means either my n2 is 0 or this whole thing is 0. Same maneuver here. I hate the fraction, so I multiply through by the LCD, which in this case was 200. Multiply through by 200, I would get this. Then I just solve for n2. Right? So now I have two values for n2. It can be either 0 or 100 or 50 over 3. But I know my n1 is this. So if I find my n2, I can plug it in here to find the n1.
Then you can
And that's what I did. So if my n2 is 0, I plug it in here, and my n1 would be that. And then if my n2 is 50 over 3, I plug it in here, and it would be that. And so that gives me two other coordinates. So there are 4 coordinates in general. Okay. That's step 1.
How many steps are there?
Like 4? Yeah, 4. Just sort of like last time. But yeah, once you're dealing with 2 equations at a time, it gets crazy. Then we're going to do 3 equations at a time. I'm kidding. We wouldn't finish the syllabus if we did that. Okay, so step 2 is to draw the null lines. Now, this is where what we were doing last time with those drawing the equations and figuring out the sign in each region. That's where that comes in handy here. So step 2, draw null lines. Okay, now if you wonder what the null lines are, let me rewrite them again. What were the equations? Okay, I had dn1 dt equals 0.2 n1 times 1 minus n1 over 100 minus n2 over 50. So that equals 0. And dn2 dt equals 0.1 n2. Okay, so here's what the null lines are. These are straight lines. How do I get their equation? Is you set the insides here equal to 0. Right? Technically, it's just like you're solving the steady states. Right? We're drawing the steady states. So you said each term equal to 0. But these guys equal 0 would just be the x and y axis. So I can kind of ignore it and only do this. Right? So the null lines, you can think of it as the insides equal 0. But we think of them as equations of lines. Okay, so this means here we need to draw 1 minus n1 over 50. Oh, that's 100. Minus n2 over 50 equals 0. And at the same time, draw 1 minus n2 over 25 minus n1 over 200 equals 0. I'm going to draw these two lines, right? Think of the n1 as the x and the n2 as the y. So I'm going to draw it on the xy plane. So this is like 1 minus x over 100 minus y over 50 equals 0. 1 minus y over 25, blah, blah, blah. So they're straight lines. Remember how we draw the straight lines? So I'm going to save space for it here. We're going to be modifying this graph, so I'm going to just put it in the middle and leave it up. So this is like my n1 axis, this is my n2 axis. So how do we draw the straight lines? Let's draw the first one. What did we do? What was the trick?
You made 2 dots.
You made 2 dots. How do we get the dots?
The points that we got in the beginning. Just kidding, no.
So 1 equals 0 at a time. That's what we did last time. You guys actually review your notes or what? Right? So if I want to find what n2 is, plug in n1 equals 0, solve for n2, I get 50. So n2 is going to be at 50. If I plug in n2 equals 0, I'm going to get my n1 equals 100. So I'm going to go here, 100, right, on the n1. And I'm going to connect this with a straight line. This is called the n1 null line. I'm going to do the same thing for this guy. Plug in n1 equals 0, I get n2 equals 25. So on my n2 axis, I'm going to get 25. Plug in n2 equals 0, I get n1 equals 200. So call that 200, and then I'm going to connect these two. This is the n2 null line. Right? It's very important you know which line corresponds to which equation. Right? So as soon as you draw it for this one, just make sure you label that n1, and as you draw it for this one, label that n2. A lot of students like to color code these lines, which is fine, but I don't like colored chalk, so I'm not going to do it. But it's fine if you color code things so that you can keep track of everything. It's going to be very important that you know which one is which. Okay? So that was step 2, to draw the null lines. Right? Leave that arrow up. Step 3 is to draw the stability arrows. However, in this case, it's going to be different from our stability arrows from the first time. To draw the stability arrows, this is where we're going to figure out the signs in each region. To that end, let me copy these guys back here. I'm just recopying this. You don't have to write it again. Just look up. Okay, so here's how we're going to do the stability hours. We're going to try to find the signs in each region of these derivatives, right? So I pick a random point in one of these regions. Let's say, what do I know is in one of the regions? Anyone? Let's do like 50. Let's do 200, comma 50. Right? So that point is in both, is in that region. Right? So I know that's in this region up here. Right? Now what we're going to do, just like last time when we were checking the signs of the equations, I'm going to plug that point into the line and see what value I get. Right? So notice that here, if I plug in 200 for N1 and 50 for N2, what's going to happen?
You're going to get 0, 0, 1. So here, and it'll be...
This I won't care because this is positive. Right? I only care about the signs, remember? So this is positive, so I ignore it. If I plug in N1 equals 200, right? This is 1 minus 2 minus 1. So it's what? Minus overall, right? So if I plug in this point, notice that my dN1 dt is negative. Plug in the point in here. Right? So I'm going to plug in, if N1 equals 200, that's just 1 minus 1, so that goes away. And so here I'm left with a negative number again. So here my dN2 is negative. So here's how the strategy goes. If dN1 dt is less than 0, you draw an arrow to the left. Right? Remember, I'm thinking of dN1 as the x value, right? So it's horizontal is how it focuses, right? So if x is decreasing, it goes to the left, right? If dN1 dt is greater than 0, you go to the right, right? Because N1 controls the x.
Did you mean dn2 over dt in the second one?
No.
No, okay.
Then, now I look at dN2. dN2 dt. If that's less than 0, you draw down, right? Because my N2 is like the y value. When y is decreasing, it goes down. If dN2 dt is greater than 0, you draw an up arrow. It means your y is increasing, you're going up. So if your x is decreasing, you move to the left. If it's increasing, move to the right. If your y is decreasing, you move down. If it's increasing, you move up. Right? So what you're going to do, once you test this point into these equations and you find their signs, you're going to draw arrows like that based on what the signs are. So in this case, my N1, which controls the x, is negative, which means here I'm going to draw an arrow to the left. And since my dN2 is also negative, I'm going to draw an arrow down. Okay. So if my solution is at this point, what is it doing? It's moving to the left and down, is what I'm figuring out, right? I'm figuring out how my solution will behave, which means its direction is sort of heading this way. Right? Any questions on this? So I draw the null lines, which I just said the inside is equal to 0. Said this equal to 0, said that equal to 0. So just straight lines, plug in 1 equals 0 at a time, plot them on the axes, draw the lines. Right? Once I have my lines, pick one of the regions, and I'm going to test the point. I test the point in these guys. And I'm only looking for the sign. Are they positive or negative? In this case, they were both negative. So this means in the x direction, I'm decreasing, and in the y direction, I'm decreasing. So my curve is moving to the left, and it's at the same time moving down, which means it's moving like that. Okay?
Wait, what's moving like that? I don't see two straight lines.
the solution curve. So now we're going to have to fill in all four. Right? We're going to figure out what this guy is actually doing. But if you remember the trick that we did last time, every time you jump over a line, you switch the signs, right? Now the reason why I need to know which line goes with which is I'm only going to switch the arrow that corresponds with the line that I'm jumping over. This line here corresponds to N2. So if I'm over here and I jump over here, I just jumped over the N2 line. So my N2 sign is going to switch. So this is not going to be negative anymore, that's going to switch positive. So my vertical is going to swap. And so over here, that would go up, and this stays like that. And so the curve goes like that. Then from here, I jump over that line, which I just jumped over the N1 line. So now my N1 is going to change.
To the right.
So it's going to go to the right. This guy stays up. So I go like that. Then I take him, jump over here. Who did I jump over? Jumped over N2. So how are things going to change? Down, stays to the right. So I'm going to go like that. These are my stability errors.
What do they mean?
Same thing the stability errors told you before. They told you what direction your curve was going. Remember?
Yeah.
So back in when we're doing only the single variable, we know that the arrows told us where to go.
Yeah, they went like this.
The stability arrows tell us if it's pointing to the right, you just move up. Right? If it was pointing to the left, you move down. Right? These arrows tell you where you're going. Right? So these arrows are literally telling you where you're going depending on what region you're in. Right? So finally, step 4. Given initial conditions.
This is also one question?
This is all one question. Yes. Plot the initial point. And follow the middle arrows to draw the solution curve. So once you go through this whole thing, and you end up here, now you can figure out how to actually plot the solution. So let's say I told you my initial condition was, I don't know, we were over here. What would I do? I would move in that direction, because that's what this arrow is telling me. I'm in the region that says move this way. So I would go, now I'll end up here. What if I was, say, somewhere like here?
So
You
to
go
the
down.
left.
I'd still go this way, but once I cross that line, what am I going to have to do?
Go
You're
up.
going up.
I'm going to turn and go up that way.
Oh, snap.
I'd still end up there. Interesting. What if I was like right here?
You're going to the left.
I would go this way, jump over that line. Now I'm in this region, go that way, I end up there. What if I'm right here?
You have to go up.
Go that way. It seems to me that no matter where I start, I'm going to end up here. Now, what is that point? Well, that was where the two lines intersect. That's actually my steady state where the two values were non-zero. Right? That's going to be, what were the answers we got here? It was, what, 50 over, like 200 over 3 or 50 over 3, something like that?
Yeah, 200 over 3, 50 over 3.
Right? So, can we determine the long-term behavior of this system?
So the 100, 0 doesn't matter.
So, in this case, the long-term behavior is the following. both N1 and N2 will survive and approach N1 would be 200 over 3, and N2 would be 50 over 3. So with these equations describing a competition model of these two species, N1 and N2, and I want to find out what's going to happen to this ecosystem, this is where it's going to end up. Both are going to survive. Sure, N2 is taking more damage than N1, right? Notice that its population ends up being smaller. Right? So all other things being equal, N2 is going to end up with less people because it's taking more damage. But overall, I can just follow my solution curves to figure out where I go. And that would be a whole problem.
Why are we not using the 200 over 3 and the 50 over 3? We have other solutions.
Because no matter where I started, that's where I ended up. Right? I started at many different points.
And
They all seem to come back to this point. Even if I'm like here, super close to 0, 0, which is another steady state, this arrow is telling me go up.
Okay.
So everyone will die out. That will never happen. So no matter what region I'm in, these arrows are telling me go there.
Okay, I understand.
So what happens now, that's the steady state. That's like where your asymptote is. You're always heading towards that point.
Every time you skip over a line, you change signs for that.
For that arrow. Yeah. Which is why it's very important that you label which line corresponds to it. Right. So once I jump over an N1 line, I change the left or right arrow. If I jump over an N2 line, I change the vertical line.
For the first part, when you chose 250, would it be okay if you chose like 25 and 200?
25 and 200 would give me, I'd still be in here. I'd get the same thing.
So it doesn't matter when you choose.
No. Just make sure whatever number you pick, you know for sure where it is. Right? So make it obvious. Yeah, so that's all for steps.
How long will this take to do?
Well, in the final, you always have 15 minutes per problem, and there will be one problem where you just do this.
There better be one.
So you could have up to 50 minutes.
And in our
15
exam,
minutes.
will we have one problem in our exam, the one that's coming up?
Well, you need. I don't remember.
Okay, do one. Just one, please.
Practice. Okay, so yeah, it's 15 minutes. If you want more time, just be super fast on another one and spend the extra time over here. But on average, you have 15 minutes per problem, and this would be one question. More examples.
Yay.
Wait, don't you raise it?
Where can I
Start with that board.
Start with the corner.
You can start there.
Before we start, some shortcuts, because this can take forever. Okay, so it turns out you can actually predict the behavior to some extent.
Yeah.
If you're R1, R2, K1, K2, well, these obviously have to be positive, but A1, 2, A2, 1 are positive, all positive, which they are. I'm not going to ever make them negative. So that's pretty much, this means always, right? Then, if you have something like this, where you have 4 regions, right? The top region here, it's always going to look like that. Always. Right? And you can just basically watch the signs. Like the inside is going to look like 1 minus n1 over something minus n2 over something else, right? So I'm always taking 1 minus 2 huge numbers, right? If my n1 and my n2 are big numbers, this will always be a negative number, right? So it's always going to be decreasing in both directions, right? Another way you can think of that is, it's the more realistic situation, right? Because otherwise, if one of these are increasing, I'd shoot off to infinity. One of my populations would get out of control, which is just not realistic, right? So, yeah, it's pretty much, it's always going to be this in the top right corner.
So it's always going to look like this.
Yeah, so you never really have to test these points, technically.
So, question, Jhevon.
Yeah.
So, after step 3, well, you don't really need step 3. What step do we draw? This thing?
Step 2 is drawing the null clients. Step 3 is drawing these arrows.
Okay, so we technically don't need to. I don't know what I'm saying.
We need all the steps here. None of them are optional. I'm just telling you about shortcuts to get through one of them, right? So this step here to draw these arrows, we usually start out by testing a point and then just jumping over the lines and switching the arrows.
Yeah.
I'm saying you don't have to test this point. Top right corner, always going to be that.
That's what I wanted to ask.
Yeah. Now the other 3, they can look different based on how your lines are positioned, but the top right corner is always going to be that. Yeah. Well, if you skip to here, you'll never figure out what coordinates you have to grab. Right? You wouldn't be able to figure out this point. What?
What if the question's going to ask for it?
It's going to ask for it. We need to know the steady states. Right? We need to know where the populations are going. Yeah.
How do you know that's 253?
We solved for it in step 1. So in step 1, we got our steady states. It was either 0, 0, this guy. What was the other one?
100,
0.25,
100,
0, 25 was the other one, which is here.
100, 0.
Or 100, 0, which is here.
And then
So it means there are 4 possibilities for where this guy's going to end up. Either everyone dies, or N1 dies but N2 survives, or N2 dies but N1 survives, or they both survive. In this situation, this particular situation, both survive. Okay. But as for a shortcut about how to get these arrows, top right corner, always going to be that guy. Just by how our equations are set up and because I'm always going to give you positive numbers for those values. Another shortcut. Maybe I can start over here. Shortcut 2 that I'm going to tell you about, it actually replaces doing the competition table. And, as a bonus, it tells you what the end behavior will be. Or I should say long-term behavior. Which is nice. A lot of bang for your buck. So I could actually know that both would have survived before I even started the problem. So I know if I do something and that doesn't happen, I made a mistake somewhere. I should go recheck my work. Right? So it's called Lois Method. It's completely non-standard. Just want to mention that. It's not in your textbook. It's not anywhere. Okay. The name was actually coined by me, but it's actually named after a friend of mine who came up with it. I'm going to show you the method now.
You guys are like the Big Bang Theory for math.
What?
You guys are like the Big Bang Theory for math.
No, he just has way too much time on his hands. Yeah, he's taught 209 like tons of times, so he just starts, you know, it's like Rain Man. He starts to see things after a while. Yeah, with this method. He's actually teaching 209 this semester as well, I think. He's Chinese. His English name is Raymond Lo. Right? So his Chinese name though is like Chi Chung Lo.
Yeah.
Right? So it's spelled weird too. It's like I don't know.
Hey, oh my god!
Right? So then he's like, yeah, like no vowels. Like what the hell?
Dude, I was
right?
trying to get into his class.
I know. That's him. This is right?
Now I'm learning his method.
So now he's like, okay, Jhevon, make sure when you tell them to do this, they have to write out the whole name. Chi Chung Lo's method. And if they don't write that, no points. They can't. No, forget that. You guys gotta remember that. I just call it Lo's method. And it's all based on patterns. So the patterns go, it's based on X.
You should patent it.
On this region, you're gonna say depends. On this region, it's both. In this region, it's N2. In this region, it's N1. Actually, I always forget which one. Yeah, it's always that. Yes, I remember. Okay, that's it. So basically how I'm going to draw arrows on these, and basically how the arrows are pointing, it's going to tell you which situation you have. All right, so for example, if you have two arrows doing this, notice that they point that way. This gives you the depends. Right? Or if you have two arrows that, this means N2 survives. If you have two arrows doing this, it means both survive. And if you have two arrows doing that, N1 survives. Right? Of course, N2 survives, I'm actually also assuming N1 actually dies. Right? So this means you're going to hit to the steady state where N1 is 0, but N2 is whatever the other number is. Right? In this case, N1 survives, but N2 dies. Right? This case, both will survive. This case, it depends. Depends is equal to competitive. Right? It's actually a competition. I don't know ahead of time who's going to win. It depends on who gets the upper hand in the first place. Right? So if my initial condition has one population much larger than the other, he could win. Or vice versa, the other one could win. I really don't know. Right? So this is really where the competition is. Right? You don't know what's going to happen. Right? But there are the other situations where N1 is the clear winner, N1 is the clear winner, or N2 is the clear winner, or they'll both survive. They're both winners. Here it's like, I don't know what's going to happen. This is competition. Right? Now what do these arrows actually mean?
Is he gonna go yell at them?
Okay, so those are what the patterns mean. You gotta shut the door, it's so hot. How did it turn summer all of a sudden, by the way? I meant to ask that. Like why is it 70 something?
It's so
Climate
beautiful
change is
weather.
Next week, don't get
I have to stop. You guys are rubbing off on me now. I can't even tell when you guys are joking. She said it's so serious too. It's like, oh yeah, there's a blizzard next week. Is there actually a blizzard for real? See, I don't know whether she's joking or not. What the hell? Okay. Here's how you draw the arrows, right? So these arrows happen on top of your equation. Arrows point towards lowest denominator. Okay, so let me explain how that actually goes. So let me rewrite what the first equation was. Was dn1 dt, dn2 dt. This is my first example. This guy was 0.2 n1, 1 minus n1 over 100, minus n2 over 50. This is equal to minus 1 n2, 1 minus n2 over 25, minus n1 over 200. Okay? So if we're doing Lois method, what would happen here, right? Look over here, right? The x is going to go right on top of this. My arrowheads will point towards the smaller denominator, right? So among these two, whose denominator is smaller?
The n1.
This one. So my arrow is going to point that way. Along this line, whose denominator is smaller? This one. My arrow is going to point that way. So this gives me that pattern, which tells me both. So now, so this means before I even do anything, I know both will survive.
Can we use this in the test?
You don't say it, but you use it.
Oh, is that a joke?
Yeah, I'm telling you so you cannot use it.
Okay.
That's why I'm wasting like 15 minutes.
I mean, is this legitimate?
So then, also,
Yeah, you use it anyway.
Can we say,
non-competitive.
can we say due to Lois method, we got this, and that's it?
Nah, change
So we won't have to.
Chi Chong Wo. And you have to say with the accent too. Chi Chong Wo. Chi Chong Wo.
That was. There was.
That's your friend, though.
I hope you see it. I'm going to show it. Okay.
You're so
Right?
happy making fun of your friend.
You might have offended someone.
He makes fun of me all the time.
What does he say?
He's just not on YouTube when he does it, so no one knows all the abuse I take at his time. Yeah.
Can you repeat how you got the arrows?
Okay, so the x go over like this. The arrows point towards the lowest denominator, right? So along this line, I look for who is the smallest denominator. I have 200 or 100. 100 is smaller, so my arrow is going to point towards the lower one. Then I look at this line. Go towards the smallest denominator. I have 50 and 25. 25 is smaller. I'm going to go that way. So I have an arrow going here and an arrow going there, and I have this. So, for example, on a test, you would write something like, by Lois method, we have so both survive and the system is non-competitive. Right? So this replaces doing the competition table. So if I say something like, oh, state whether the system is competitive and justify your answer, you could write that, right? Or if you prefer to use the table, you can do the competition table and say, oh, this is not greater than that, so it's not competitive. Either way, I don't particularly care which method you use.
So we skip step 4 and we do this.
So,
I mean,
no, I still might want to know what the solution curve looks like. I still might ask you to draw it. But at least you know where you're going. You know what should be happening in the end, right? So once in step 1 I found all 4 steady states, this is going to tell me exactly where I'm going to go. I know I'm going to go to the steady state where both coordinates are non-zero.
not on the line.
Right, so it'll be where the lines intersect. It won't be on the axis.
Yeah.
Right? So this is called Lois method. That's a shortcut. Any other shortcuts? No, we don't get away with much here. That's pretty much it.
Just because it's a night class?
Let's do some more. It's because it's a night. Let's do some more examples so we really get into the groove. Because, like I said, it's kind of like curve sketching, right? The problems take forever. So you just really want to do them over and over and over until you get used to doing them. So, where can I erase?
Everywhere.
Everything.
So remember the original question. 1, tell me if the system is competitive or not, and 2, determine the long-term behavior qualitatively. So this is the my second example.
We can answer A by Lois Method.
You can answer A by Lois Method. So this is my second example. dn1 dt equals 0.3 and 1. So in part B, I had 15, 50, and 25, 20. Okay, so tell me, is this competitive or not? And then analyze qualitatively what's going to happen.
Okay, so the first arrow is going down to the right, and the second
So
arrow
if
is
I do
going
this,
exactly,
this is
So
going
and
here,
and then
one
to the
circle.
left.
and here.
Go
And
one
one
to the
to the
left.
That means N1. So you say by Lois Method. We have boom, boom, boom. So the system is not competitive. And furthermore, I can even predict who's going to win. N1 survives. Let's actually see if that's true. So now we're going to go through step 1, steady states. So if I set this equal to 0, and that equal to 0,
Why are you saying that it's not competitive?
Because only one survives during Lowe's method.
only one's going to survive.
We know that from Lowe's method.
Doesn't that make it competitive?
How's that competitive?
Because one survived. So that means they have to be competition.
Isn't that a competition?
The competitive is when like they're like
When
equal
it's-
match kind of.
Yeah,
right?
it's actual competition.
But you said when they both win, there's no competition.
Right.
It's only independent, so it would one would have to go to the top right corner.
Basically, if you can predict the outcome, it's not competitive. Basically.
So if it lands on the fence, then it's competitive.
All right, think of it. Mike Tyson versus a 5-year-old.
Oh, the fence.
Who knows who would win? Mike Tyson. Is there any competition? No, because you know Mike Tyson is going to win. It's
Am
no
I gonna
competition.
call
versus that
CPS on
5-year-old.
him? Yeah.
Right?
It's the child.
Right? If you can predict who's going to win, yeah, he's definitely going to win because that guy's never going to beat that guy. It's not a competition. Right? The only competitive case is the depends case. It's like, whoa, depends.
That makes
Mike
great-
Tyson versus Holyfield. Depends on who gets the first hit in, right? You don't know what's going to happen. It's just like, you know, if one of them slips, you never know. You know, you catch you slipping, you just, you know? So that's competition. It's not competition kind of, oh yeah, anyone's definitely going to win. There's no competition there, right? So now let's actually go to steady states. So we're going to set each of these equal to 0. So from 1, I get n1 equals 0, or 1 minus n1 over 50 minus n2 over 50 equals 0, which means my n1 is equal to 50 minus n2. Right? So there are two situations. Either n1 is 0 or n1 exists. So now, in 2, if n1 equals 0, what's going to happen in the second equation? So in the second equation, if n1 equals 0, this term disappears. And I'm basically going to have n2 times 1 minus n2 over 25 equals 0. Which means my n2 equals 0, or n2 equals 25. So now I have two steady states, 0, 0, or 0, 25. Those are two steady states. In 2, if n1 equals 50 minus n2, then the equation I'll end up with is n2 times 1 minus n2 over 25 minus 50 minus n2 over 25. So now, either n2 equals 0, or this whole thing equals 0, which I could multiply by, what's the LCD of 25 and 20?
25.
25,
I don't know.
100.
100 is the LCD of 25 and 20. So I'll multiply this whole thing by 100. I will have 100 minus, this
4.
25 would cancel out, 4 and 2.
So it is
Minus.
5 and 2.
This will give us 5 times 50 minus n2 equals 0. So here I have 100 minus 4 and 2 minus 5 times 50 is what? 250 plus 5 and 2 equals 0. So I have 5 and 2 minus n2, that just gives me n2. 100 minus 250 gives me minus 150, which I bring to the other side. And it becomes positive 150. So in this case, my n1 would be, I put it back in here. n2 is 0, so my n1 would be 50, and I end up with 50, 0. Here, to plug it in here, I would have my n1 equals what?
Wait, how did you get, can you go back to, how did you get 50 from N1?
I have this equation here.
Oh, okay.
n1 is 50 minus n2.
Okay.
So where my n2 is, I plug it in here, and I get that back. So this would be negative 50? Negative, it's 150, so negative 100. So another steady state is minus 100, comma 150. So step 2, we're going to draw the nullines. Right, so you automatically see here right away, both surviving is not going to happen. Right? You have a negative here. So either one of them or both of them has to die. Only these 3 would apply to a population. So I know it's not even possible to even think that both would survive. But is it true that n1 will actually survive? Let's continue. So now we're going to do step 3. Draw those nullines. And
You said 2.
That's step 2. And step 1 took forever, right? Step 2, we're going to draw those nullines. I'm going to want to make sure I can get a minus 100 in there. So let's go a little bit over here. So remember what the nullines are. You take the insides. I erased the thing. You take the insides equal to 0. So I have 1 minus n1 over 50 minus n2 over 50 equals 0. I'm going to plot that. Notice that if you cover up n1, you solve for n2, you get 50. So one of those guys are going to be 50. And if you cover up n2 and solve for n1, you also get 50. So this guy here is my n1 nullline. In the second line, if I cover up n1, I get n2 equals 25. I'm going to need more space. Hold that thought. Lois. Okay, so now in the second equation, if I cover it, N2 would be 25. N1 would be 20. So this should go like. Right, so this here is going to be my minus 100, comma 150. Right? So my possible steady states are the origin, either they both die, or I will go to 50, comma 0, or they'll end here, or I will end up here. Right? Technically this is a steady state, but for populations it's not very realistic. So, yeah. Now Lois Method says this is where we're going to end up. Let's actually figure out if that's true. So we're going on to step 3. I know this top right corner is going to be that. And this was the N1 line. This was the N2 line. So if I take this and jump over here, what changes?
The N1.
The N1. So I'm going to go left and down. And if I jump over here, what changes? N2. So it goes up and then. If I jump over here, what's going to happen?
If you jump over what?
If I, from
So
this
N1.
region, I jump over here.
So N1, so it goes to the left and up.
So N1, so it's going to go left and up. So it goes that way. So I'm going to give you an initial condition. Populations, obviously I can't be over here in the negative, so I'm going to ignore that. I can't be under here. So my possible places are what?
The axis.
I could be here, super close to the origin, but we still start with both, right? Now what would I do if I'm there?
Well, you move up.
I would move
to the
up
right.
according to this arrow. So I would go up. But now I enter this region. What am I going to do?
Well, you know, you
Go
go
to
to
that
the
way.
right.
Hit that steady state. Well, what if I'm over here? Okay. What if I try to hit this one? So I go super close to it. I'm going to go down. But then I'm going to come in this region and go.
We're gonna end up at the.
We're going to end up there. And one's going to survive and two's going to die.
So it's at 50, 0.
So depending on where I give you the initial condition, it seems to always, once I give you any positive region, we're heading to the 50.
You can't be in the negative because population can be negative, right?
Right.
Okay, so
It's not a realistic situation. N1 and N2 in general represents population, so this whole region here, we don't care about usually. How long did that take?
No, we're looking at
Right, yeah, well, the first time. What? I think so, right? So like 10 minutes.
It took us, because he's going to try to fit in another one. About a good 30 minutes.
No, we totally have enough time for another one.
You should probably let us up.
right here.
Yeah.
Okay, yeah.
You don't really got much else.
Let's say we're here.
I'll tell you what, if I tell you what my next 2 exams are, do you guys promise to try them on your own at home?
Yeah, I promise.
Now, what is
I
this?
promise.
Yes. Thank you.
We have a quiz on Monday, so if you don't want to practice, I'm okay with it. I'm actually okay with it. You guys don't have to practice if you want.
I'm going to do better.
Here are the next 2 examples we're going to do. Try them at home on your own to see if you can figure it out. And we'll go over them on Monday.
Jhevon, you could post the quiz.
What?
I'm just a dumb fuck. Like,
No.
there's no help.
So my 3rd example would be, hey, settle down, quiet. dn1 dt equals 0.2 n1 times 1 minus n1 over 50 minus n2 over 25.
This is another problem.
So who knows? Who knows about Lois Method? Is it just you and Lo?
Yeah, I guess.
You gotta keep it on the low though.
I'm gonna use that one. That was great.
Oh man.
Gotta keep it on the cheech on low. Stop laughing at my friend. Come on. You guys are so horrible. Look how much work he saved you, and you guys are just my goodness. So ungrateful.
You were like karate chop in the air.
What?
He did the low bed.
What are you talking about?
It's on camera, so you got it.
Nope.
He hasn't power
No, he's probably
I do not see anything on camera. Into over 50.
Wait, what is
So
this
you need
concept?
4 and not D.
Imagine getting drinks with Lo.
What?
Because you wrote D.
Yeah,
I'll
what-
start doing math. Like,
Where did I write D?
Right there. Right next to D and you on the
On
bottom.
the second one, what is that?
No, right.
What number is this that we're doing?
4. Number
Oh,
D
4.
or number yeah.
That's valid.
Just wanted to make sure.
Oh, we're just, these are practice questions.
where are you going to post these solutions?
I'm not. You guys are gonna do this.
Where are you going to post those solutions?
So these are the problems.
And when
Go and try those on your own. We have a quiz on it on Monday. On Monday we will finish this chapter, which means the next test will be the following Monday.
are we done?
Wait.
So there's no homework.
Wait, is this?
Are we
There's
still
no
karate
homework
chopping
on Monday
No.
because we did not finish.
Monday we finish this and
Monday we're gonna
Wednesday's
finish this,
review.
which means the homework for this chapter would be due on Wednesday.
Uh-huh.
But then the test would be a week from now.
So what are we doing?
And Wednesdays are quiz.
So
Monday, we're going to do a quiz. We're going to finish this. We're going to have tons of time left over, so I'll probably move on to the next chapter. Wednesday. We'll review after you guys actually do the homework and get some practice. Anyway, get out of here. You guys are wasting my time.